Hello, my name is Yuan Tian. In this video, I want to introduce our paper toward autonomous robotic micro-suturing using optical coherence tomography, calibration, and path planning. The micro-suturing is a basic skill used in microsurgery, but it is tedious, time-consuming, and surgeons need long-time training. Robots, such as Da Vinci system, can alleviate surgeons' burden, but the autonomous suturing is still challenging. For example, for normal camera, when the needle is under the tissue, the vision system cannot track the needle. During the needle insertion, due to the large deformation on the wound, it is hard for the robot to track the movement of the planned entry and exit points. We also need a micro-resolution imaging system to calibrate the needle and the camera. The previous autonomous suturing robot's suturing error is larger than 1 millimeter. Our goal is to develop the autonomous surgical suturing system, and the needle insertion error is less than 1 millimeter. We present a robotic suturing system with the guidance of the optical coherence tomography, OCT. OCT is the laser-based imaging technology. It can generate the cross-sectional view of the biological tissue. We call this B-scan. With several B-scans, we can generate a 3D OCT volume of the biological tissue. OCT has micro-resolution. With OCT, our suturing accuracy is 0.2 millimeter. In the right image, this is our surgical suturing system setting. In our system, there are two hard points. The first is the small OCT working space, which is less than 1 cubic centimeter. From the block diagram, to autonomously sample different needle poses in OCT volumes before the calibration, we need to avoid the needle going out of the OCT volume. Another point is that before the needle insertion, we need to adjust the OCT scanner's position to make sure that the top layer of the wound is in the OCT volume, which introduces the OCT scanner position uncertainty. We also need to mount the needle on the needle driver. We cannot make sure the needle's position on the needle driver, which also introduces the needle grasping uncertainty. Therefore, we need to calibrate the needle and the OCT scanner. To achieve the sub-millimeter suturing accuracy, we need to calibrate the needle frame and the OCT frame. We let the robot move to M different poses, yielding paired observations TICPI and TEEI. The TICP is the transformation matrix representing the needle frame in the OCT frame. We can use ICP algorithm to calculate the TICP. From the formula, we can use another way to represent the TICP. The inverse of the TOCT, representing the robot base frame in the OCT frame. It multiplies with TEE, which representing the robot anti-effector frame in the robot base frame. Then it multiplies with Tian, which representing the needle frame in the robot anti-effector frame. With the Liebenberg-Marquardt method, we minimize the error in this equation over Tn and TOCT. For every calibration trial, we also record the translation root mean square error and the rotation root mean square error among 9 needle poses. The next step is to generate the suturing path. We use MO to find the top layer of the wound. MO is an image segmentation algorithm to detect the top layer of a macular hole on human retina. We use this technology to detect the top layer of the wounds on the porcelain skin or the tissue phantom. The next step is to identify the key points on the wounds. There are 3 key points on the wounds: the left edge, the right edge, and the deepest point. After we calculate the top layer of the wounds, we use a Gaussian kernel to denoise it. Then we calculate its gradients. We start search from the left to the right on the gradient. When the gradient is less than the threshold, we suppose this is the left edge. We start search from the right to the left. When the gradient is higher than the threshold, we suppose this is the right edge. We always suppose that the lowest point on the top layer is the deepest point of the wound. With these 3 points, we can define the right exit points and the left bite point. With the left bite point and the right exit point and the needle radius, we can calculate the suturing center. With the suturing center and the needle radius, we can generate the circular suturing path along the B-scan plane. In the experiment, firstly, we let the needle follow the arc in the air. In this video, there's no suturing target. We need to check whether the needle follows our desired suturing path. The red curve is the needle desired inside surface path. The green curve is the desired needle tip path. The blue curve is the desired outside surface path. But we can never see the outside surface because the laser cannot go through the metal. From this video, we can see that the needle follows our desired suturing path with relative low error. Then we let the robot insert the needle into the suturing target. In this video, the suturing target is tissue phantom. During the insertion, the needle driver blocks the part of the top layer of the tissue and the part of the needle. There's a refraction between the tissue and the air. During the insertion, there's a huge deformation on the tissue, which is hard for us to track the movements of the planned entry and exit points. Due to these reasons, it is hard for us to implement a closed loop control. Instead, we use open loop control. The result shows that the suturing accuracy can still achieve our requirements. After the needle insertion, we manually mount off the needle from the robot and pull the needle out. The suture will go through the wound, and the top layer of the wound will approximately go back to its original state. We calculate the suturing root mean square error on the intersection between the suture and the suture target. The yellow curve is the desired top layer of the suture. We made the insertions in the tissue phantom and the porcelain skin. We calculate the root mean square error on 4 grading points. For the tissue phantom, the total root mean square error is 0.177 millimeter. For the porcelain skin, the total root mean square error is 0.290 millimeter, which is less than the half width of the needle. We also did a mounted throw. These 2 images are the top-down view of the mounted throw on the tissue phantom. The upper image is in the normal camera. The lower image is in the OCT volume projection. Between every throw, we manually mount off the needle and pull the needle out. Then, we manually remount the needle on the robot. The robot will redo the calibration and made another round of the needle insertion. The green line in the OCT volume projection is the one of the B-scan's position, which is shown in the following image. After the mounted throw, we pull the 2 sides of the suture to close the wound. Among the second throw's entry and exit points, the wound is totally closed. From the B-scan view, there's no dead space after the wound closed. We also did the mounted throw on porcelain skin. After close the wound, there's also no dead space. For conclusion, we present an OCT-guided microsurgical suturing system to autonomously guide the needle into the soft tissue. The position is approximately half width of the needle between the planned and executed entry and exit points. For the future work, after we overcome the shadowing, the refraction, and the deformation of the tissue, we can add a closed loop control into our surgical suturing system. It can improve our suturing accuracy. Thank you for your attention.